Hello, this is Ayça. Today I will present you a dynamical model of action selection and dopamine-related movement disorders. As you might know, the voluntary actions are executed by the basal ganglia cortex thalamus loop, and we proposed a model for this loop as given in this diagram. This is the cortex, and these are the basal ganglia subunits, and this is the thalamus. So we have the direct and indirect pathways controlling the decision of this model. So our model can choose either to initiate an action or not to initiate an action. Also, one of the main regulators of this mechanism is dopamine, which is found in the corticostriatal connections. Abnormal levels of dopamine are related with multiple, various movement disorders. Today, we will take two of them into account, namely Parkinson's and Huntington's diseases, which I will talk about them in detail later. So we have expressed this model in the continuous nonlinear differential equation set. We have assigned two variables for each of these boxes here because we wanted to represent two different actions. So our model can choose either one of these actions. It can choose neither of the actions or both of the actions. So this stimuli is given to the cortex, and we read the output from the cortex. And at the steady state, if a cortex variable has a greater value than a certain value, we assign that decision actually as our model choose to execute the action related to the action of that channel. Yeah, so also we represented the dopamine parameter as theta in this activation function. So let's jump to the domain of attraction analysis. Here we have on X and Y axis, we have the initial conditions for the first and second cortex variable. Each dot on these graphs represent the decision of the model at given conditions, initial conditions. So the gray dots represent none of the actions are selected, whereas the green dots represent the cases where both of the actions are selected. Blue and purple color represents the first and second actions are selected respectively. So we have conducted this analysis for different values of stimuli pairs and different values of the theta, namely dopamine parameter. As you might notice, when theta is equal to 0.1, none of the actions are selected, no matter what the initial values are. On the contrary, when the theta is equal to 0.95, both of the actions are selected for all of the initial conditions. Actually, these correspond to the Parkinson's and the Huntington's diseases, respectively. So in Parkinson's disease, patients struggle to initiate an action, whereas in Huntington's disease, patients struggle to stop an executed action. So, and we have intermediate values, which we observe a gradient in the behavior. So when both stimuli are equal to each other, we have a symmetrical behavior, like in these two cases. But if one of the stimulus is greater than the other, we see our model chooses that action over to the other. And we can also say that when theta is equal to 0.5, this resembles a healthy condition. So we have modeled voluntary action selection depending on the stimuli, the dopamine parameter, and the initial conditions. We have played around with dopamine and modeled two of the movement disorders related to basal ganglia. And what we can do next, we can try to implement deep brain stimulation as a treatment of the diseases, and we can also implement the model on a hardware. Thank you for listening.